Good day, dear colleagues. Today I would like to present you insights into experimental techniques and give you some scientific examples of using X-ray absorption spectroscopy, which researchers can do at Synchrotrons. I believe that after my presentation, you will understand what kind of available techniques X-ray absorption spectroscopy could be, and in the future you will use this technique for measurements of your samples, and it will allow to boost your research in the future. In order to provide you to the world of X-ray absorption spectroscopy, let's speak about the basics. If we speak about X-ray absorption spectroscopy, we need to understand what absorption means by itself. Imagine that you are sitting on a sunny beach close to the sea and you are using sunglasses. Your sunglasses decrease the intensity of sunlight which is going to your eyes. The same we could present with this schematic representation, that we have the intensity of a light with I0, it coming through to the object with some defined thickness, and its intensity decreasing, and we can define the absorption of this material or of this sample by a very well-known Lambert-Beer law. As we know, and as we speak about light, about electromagnetic radiation, and about synchrotron light or synchrotron radiation, we know that electromagnetic radiation exists in a big range of wavelengths or frequencies, and actually wavelengths and frequencies connect with the energy of the photons or the energy of electromagnetic radiation by the equations presented here. And when we speak about synchrotron radiation, we used actually use the values of energy of synchrotron radiation. And if we could see here on this blue frame, we could see that synchrotron radiation exists in a very wide range of energies of photons or of photons which can be produced by the synchrotron as the machine. And using this synchrotron radiation, we could investigate the structure of a material of our samples on the level of molecules or atoms. And we can do it very precisely because of the unique properties of synchrotron radiation, such as we already discussed, a wide spectral range, which lies from infrared to hard X-rays. It's exceptionally high intensity, because if we see here, we could see that the intensity of synchrotron radiation is much higher than the conventional laboratory sources of different radiation which we have in our laboratories, or for example much higher than the solar radiation which we have on our Earth. Also, synchrotron radiation has a very unique parameter which is called as collimation. So it is a highly collimated beam we use during our measurements at synchrotron. It also has a high coherence. And this property of synchrotron radiation allows us to make images of our objects with a very high contrast in comparison to the images which we can get using the radiation without such kind of a high coherence. And if we speak about X-ray absorption spectroscopy, we need to understand how actually X-rays interact with our sample or with our material. For example, if we have an incident X-ray beam which is coming to our sample, part of this beam will be transmitted through the sample, and it will be transmitted X-ray radiation. Part of this radiation will be elastically or inelastically scattered from the sample, and part of this radiation will be absorbed by the sample, and as a result of the interaction of X-ray radiation with the sample, we will have, and as a result of the radiation, and as a result of absorbed radiation by the sample will emit electrons and will emit photons, and these photons will be called as fluorescence or fluorescence radiation. And detecting these transmitted X-ray photons or fluorescence radiation or detecting electrons, we could measure the response of a system as a function of incident X-ray photon energy. And it will allow us actually to define the absorption coefficient of our material. And for example, when we use transmitted X-ray photons, we use it in the case when we have a high concentration of the absorbing element. In the case, if we could not detect transmitted X-ray photons because, for example, the sample is very thick, or for example, the concentration of the absorbing element is very low, then we use fluorescence radiation in order to define the absorption coefficient. And in the case when we are interested in the surface parameters of our material, what is going on the surface, then we could measure emitted electrons, and it will give us information of the depth around 10 nanometers, what is going on the surface of our material. And when we make measurements of X-ray absorption spectroscopy, we not just defining absorption coefficient as it is, we are defining it as a function of incident X-ray energy. And we plot such kind of a dependence which is presented on the slide. In order to choose a defined energy from the wide range of synchrotron radiation light, we use such devices as monochromators. Monochromator actually allows us to choose exact energy of the photons in this present moment of time, and step by step we are changing the energy and detecting how the absorption coefficient changing as a function of incident or as a function of energy of incident X-ray beam. And if we look on the dependence on view how this absorption coefficient function looks like, we see that when the energy of the photons increases, the absorption coefficient, when the energy of the photons increases, we could see that absorption coefficient decreases till some kind of a moment when we have an abrupt increase of the absorption coefficient. In this case, we say that it is absorption H. And we could see that on this function we have M absorption H, L absorption H, or K absorption H. What does it mean and why it looks like this? Very simple, because we know when X-ray radiation interact with material, it is mainly interact with the electrons of the atoms. And with increasing the energy of X-ray radiation, the interaction decreases till the moment when the energy of X-ray radiation equal or higher than the bonding energy between electrons on the core levels and the nuclei. When actually we achieve this value of energies, we could excite these electrons from the core levels, and could excite these electrons to the unoccupied states or unoccupied levels, or excite them to the continuum. In this case, material start to absorb very intensively, and that is why we have an abrupt increasing of the absorption coefficient. And taking into account that it depends on from what kind of a core level we excite the electron, that is why we have the names of the absorption edges, like K absorption H, L absorption H, and so on. What is quite interesting, when we look very precisely on these absorption edges, we could see that they have a quite developed substructure. We will discuss why such kind of complicated structure appeared, but for now we just need to understand that analysis of these, let's say, oscillations which we could see here allow us to investigate the local structure and electronic structure of the materials. And what is also very important, these absorption edges or absorption spectra are specific to each chemical element. It means that we could investigate the atomic environment of each type of atom in a very complicated material separately. It means, like here, you could see that even if our material will consist from different metals, for example, chromium, manganese, or iron, it means that each of the atomic environment of each element we could investigate separately. For this, I prepared some kind of an animation. That imagine that we have some kind of a material which consists of nickel, wolframium, and oxygen atoms. And let's imagine that this material is, let's say, a small solar system with its planets. And as we know, on each planet we could have a small prince. And imagine that, for example, when we radiate our sample by some photons with defined energy range, or for example with defined frequencies as it shown here, we could communicate with the small princes which are sitting on the planets, which is called nickel. And then these small princes could give us information about about their planet, for example, about the oxidation state of nickel, about its electronic structure, and also about the local structure of nickel in the system. For example, these small princes could say us that, okay, in the first coordination shell, I could see 6 atoms of oxygen. Further away, I could see planets which is called Wolfram or nickel. Then we got this information, we analyzed the local structure of nickel, and if we change the range of energies, and for example, communicate with the small princes sitting on the planets which is called Wolframium, and then we could get the information what is going on the planet named Wolframium, about its electronic structure and about its local environment. What is also very important, we could investigate the materials in a different states of condensation. For example, for solids it could be amorphous or crystalline, it could be liquids, or it could be gases. Also, what is very important, we could investigate, for example, making ex situ experiments. But we also could make some kind of interactions with the material. We could change temperature, we could put our samples to different gas environments, we could change voltage, we could change pressure, and so on. In this case, these experiments are called in situ or operando. And we also could investigate how the structure of our materials changes when we change the parameters in which our samples are. And in order to understand and analyze the absorption spectroscopy spectra, it is better to understand what is going on with the electrons when they are excited from these core levels. And we know that these electrons can be excited to either partially filled valence band, could be excited to unoccupied state, or could be ejected to the continuum. And actually these transitions are governed by a dipole selection rule, if we speak about transitions inside the atom. For example, these dipole selection rules dictate which transition are allowed or forbidden. And we know that transition is allowed if we have a conservation of angular momentum ±1. And here you can see in the table what kind of a transition are allowed in the case of K or L edges. And if we have a closer look on the X-ray absorption spectroscopy spectrum, we could see that there are 2 ranges, and analysis of these 2 ranges could give us a lot of information about the material. One of them, it is Xane's X-ray absorption near edge structure here, and here we have extended X-ray absorption fine structure. And you can see that Xane's region has such kind of a substructures or sub-features, which is called pre-edge and rising edge. If we have a closer look on them, let's discuss what is going on with electron when we actually measuring in the energy range close to this pre-edge and to the rising edge. If our energy is quite low, then in principle atoms do not interact with this radiation much, and nothing is happening. And when we increase the energy of incident X-ray photons, we could excite our electron from core level, let's say 1s for this material, vanadium 205, to 3D level. But we know that according to the dipole selection rule, this transition is forbidden. But happily, we have such kind of an effect which is called 3D level and 4P level hybridization, and that is why, thanks to this hybridization, this transition became allowed. And that is why we could see such kind of a pre-edge feature. Then, if we increase our energy further, we could excite our electron from core level 1s to unoccupied state 4p. and it is, let's say, dipole allowed, as we already know, and that is why its probability is much higher, and that is why it is, let's say, calling rising edge, because it's quite intense in comparison to the rear edge. And here you can see some kind of a schematics of such kind of a transitions. Okay, but if we increase the energy of incident X-rays further, then we could excite our electron to the continuum. In this case, we could speak about the electron as a wave. And this wave will have a wave number, which could be calculated using this formula. And okay, this wave will go out from our absorber atom, and if this absorber atom is isolated from, let's say, other atoms, this outgoing electron wave will just go out from the absorber atom. And nothing will happen, and if we measure such kind of absorption spectrum, we see that we have features corresponding only to the transition between from the core level to unoccupied states. But in the case, if around our absorbing atom we have neighbor atoms, this outgoing electron wave will be scattered from the neighboring atoms. And this scattered electron wave and outgoing electron wave could definitely interfere with each other. And taking into account the distance between the atoms do not change during the measurement, changing the wave number of outgoing electron wave, we could probe actually the distance between the atoms, because actually we could analyze where this constructive and destructive interference appear. And here you could see what is going on and how we could investigate this constructive and deconstructive interference of outgoing and scattered electron wave. For example, if we have a constructive interference of outgoing and scattered electron wave on the level of the absorber atom, we have increasing of absorption coefficient. If we have a destructive interference, then we have a decreasing our absorption coefficient. And if we look precisely again to the XANES and EXAFS region, we could see that in XANES region, we actually analyze what is going on with the electron when it is travel inside the atom, so it corresponds to the transition between core level and unoccupied states, and also multi-scattering event. It means that we have an absorber atom and the outgoing wave going to the neighboring atom, it is scattered from it, going to the absorbing atom and going to it back, or different geometries of such kind of a multi-scattering. And actually this information is lying in this XANES region. In the case of single scattering, is using in the range which is called EXAFS. Here actually we mostly analyze single scattering events, where we have outgoing wave, it is scattered from the neighboring atom and coming back to the absorbing atom. Okay, taking into account then that XANES region contains this information about transition and multi-scattering paths, then we can say that analysis of XANES region of the absorption spectrum, we could get information about the formal oxidation state, because it's actually the electronic structure of the atom. We could get information about geometric arrangement of neighboring atoms, so we could get information about local site symmetry, and we could get information about unfilled orbitals and their electron population. Okay, and let's have a closer look on the pre-H features of the spectrum of the oxides. We see that for vanadium 203, the pre-H is less pronounced than in comparison to vanadium 205. Why it is like this? As we remember, the pre-H appears in the spectrum due to 3D 4P hybridization of the levels, and the higher the hybridization is, then the probability that we will have such kind of a transition will be higher. And we know that the hybridization is higher in the case when the symmetry of the system is lower. So in the case of vanadium 203, which actually placed in the center of octahedra, the symmetry of the system is quite high, and that is why the hybridization between 3D and 4P levels is not so high, and that is why the probability of this transition is lower in comparison to the vanadium 205, where the symmetry of the whole system is much lower, and that is why the hybridization is higher, and therefore the probability of such kind of a transition from 1S to 3D, which is hybridized with 4P levels, is higher. So such kind of analysis in a very easy way allow us to investigate the local site symmetry of our system. Also, the analysis of Xein spectra could give us information about unfilled orbitals and their electron population. For example, here we could see L3 absorption edges of 5 different 5D metals, starting from rhenium up to gold. And actually, we could see that the shape and the intensity of the white line is related to the available density of states of unoccupied levels. The higher unoccupied density of states in the material, the more pronounced white line will be, because the probability that the electron will be excited to this state will be higher. Also, analysis of Xein spectra could give us information about different oxidation states or even the ratio of chemical species present in a mixed valence compound. For example, here we could see different reference compounds of sulfur, and we could see that each chemical compound has a very unique view of Xein's spectrum. And if, for example, we have a mixed valence compound, we could make a linear combination fittings of such kind of a reference compound, and we could very precisely investigate what is the proportion of sulfur atoms, in this case, for example, for sulfur, we have in our mixed valence compound. For example, here we have a mixture of different sulfates and sulfides, and we could precisely understand what actually is the proportion of pure sulfur, sulfides, and sulfates in our system. And let's go to the practical application. One of them is actually an example which allows us to investigate the quality of the air in Krakow. Here on the slide you can see filters which were used in order to get the sample, so to get the particular matter from the air. This white filter was placed to the roof of a AGH University building in the morning, and that's how the filter looks in the evening. The researchers investigate the elemental composition of actually the dust, and then they came to the synchrotron and measure X-ray absorption spectra of these filters at sulfur KH. And analysis of such kind of a spectra just by fingerprinting or just comparing the sulfur KH spectra, which correspond to the samples gathered in winter and in summer, allows us to investigate what is the composition of this, let's say, dust or particular matter. And we found that in summer, in air we mainly have sulfates. But in winter, we have disulfates and also organic compounds of sulfur and sulfides. Measuring at another KH, in this case of potassium, allows us actually to prove that in winter samples we actually have these disulfates. And also measuring at other H, for example, iron KH, allows us to prove that we have these sulfates, and for iron, for example, we have different type of oxides and hydroxides in air during summer and winter. Another example, how actually analysis of the Xane spectra allows us to investigate what kind of a chemical composition, chemical phases appeared in our sample during the operando measurement. For example, here we measured what kind of sulfur compounds appeared in lithium-sulfur batteries during charging and discharging. In order to make this analysis, we measure different sulfur compounds, and as we already discussed, that each chemical compound has a very specific spectrum. Here you can see different compounds which we have measured. Also, we measured spectra of working battery during charging and discharging. Here you can see the maps, and if we have a cross section of these maps, you will see actually the absorption spectra. And analysis and making linear combination fitting, which we already discussed, of this spectra, we could investigate what kind of compounds appeared during charging and discharging of the battery. Okay, now let's go to the EXAFS region. We already know that when we work with Xanes, we investigate what kind of transitions appeared inside the atom when we irradiate our sample by the X-ray photons, and what kind of multi-scattered effects appeared in the sample. But when we analyze the region of the spectra at higher energies, actually it corresponds mostly for single scattering effects. And analysis of this region of the spectra allows us to identify the nearest neighbors around our absorber. We could also investigate coordination number of nearest neighbors, could investigate interatomic distance and bond length disorder in static and dynamic. In order to provide such kind of analysis, we need to normalize our X-ray absorption spectrum and actually take such kind of oscillation function using actually this formula and plot this oscillation function in a K space or weight number space. This region of intense oscillations we analyze when we analyze Xane's region. These oscillations which are not quite pronounced, we analyze when we make a EXAFS analysis. In order to make these oscillations more pronounced, we multiply this oscillation function to weight number in square or weight number in cube. And then we could see that these oscillations became more pronounced. And what it is the oscillation function, and we could make a Fourier transformation of this function, and if we do it, we could transform this oscillation function made in K space to a real space, and analysis of these peaks which we get after the Fourier transformation allows us to investigate the interaction between the absorber atom and the atoms in the nearest coordination shell. For example, for vanadium 2 oxide, we could investigate the interaction between vanadium absorber and oxygen in the first coordination shell, and also investigate the interaction between vanadium in the sample. Making analysis using different software programs allows us actually investigate the local atomic geometry in the range of 5 angstrom from the absorber. We could also identify nearest neighbors, so it means that what kind of atoms we have in the first coordination shell. For example, we could investigate that it is in the first coordination shell we have oxygen, not a vanadium. We also can identify the coordination number of the nearest neighbors. We could investigate the distances between absorber atom and atoms in the first and second and the third coordination shell. And we also could investigate the bond length disorder which we have in our sample. Okay, let's go now to the practical application of EXAFS. For example, we would like to investigate the molecular structure of copper phosphonate groups ensured inside mesoporous silica channels, as it is presented in the scheme, using Xene's spectra, we could actually investigate what was the geometry of the molecules, and let's say modeling of different geometries and applying linear combination fittings allows us to understand that it could be 3 different geometries of the molecules. Then, using these models, we could investigate precisely by fitting of the EXAFS data what is the distances between copper atom and oxygen atoms in the first and second coordination shell in our molecules, and also to understand what is the distance between copper and phosphor atoms we have in our molecules. So, as you can see, we could precisely investigate the local structure of a quite complicated molecule anchored in a very complicated system. Also, for example, we could investigate how the local structure of solid oxide cells changing depend on what was the annealing temperature. Firstly, the researchers investigate actually the oxidation state of cobalt in these solid oxide cells, and then using EXAFS analysis, they investigate the interaction between cobalt atom and oxygen in the first coordination shell, and they managed to investigate the coordination number and the distance between cobalt and oxygen in these solid oxide cells depending on the applied annealing temperature. And actually also making such kind of a wavelet transform imaging, let's say making such kind of a mapping, allows us to investigate how the interactions between cobalt and oxygen and cobalt and metals interaction in the material changing depending on the annealing temperature. Also quite interesting example, investigating of a complex molecule which could be used for memristor devices. At first, the researchers used Xene's region of the spectrum in order to see if the geometry of copper could change during the operation of such kind of a material. And we see that no changes appeared. It means that the material works quite stable. And using EXAFS data, the researchers were able to investigate the local structure of nickel in such kind of complexes. For example, they were able to investigate the distances between nickel atom as an absorber atom and atoms in the first, second, and the third coordination shell. And also they were able to investigate the coordination number in these complexes. Thank you for your attention.